Let's start. So for this last lecture, I want to discuss local limits of certain model of random maps, and more precisely, I want to consider local limits of random maps with a boundary. Okay. So what we want to construct is a infinite triangulation with an infinite boundary. So it will be, so to speak, a triangulation in the half plane, and we are going to construct it as a local limit of triangulations, random triangulations of boundaries that become larger and larger. Okay. So I want to start with the law of this random triangulation that I want to call Boltzmann triangulations. And first of all, I start with a definition. So let m be an integer bigger than 2, and a rooted map is a triangulation of an m-gon if it satisfies the following properties. So the root face has degree n, and its boundary is a simple curve. Okay. And second property is that all other faces are triangles. Okay, so and in fact, I'm going to also assume the extra hypothesis that is not strictly needed, but that is convenient. At least that's an hypothesis that you may want to make, which is there are no self-loops. And the reason is that the enumeration formulas for such objects are slightly simpler than when you allow self-loops. So it's not really something that is so important here. Okay. So I don't think I made this point last time when I think we already introduced the family of such objects. But what's important, one thing that is very important in the definition, is that the boundary, which we call the outer face, so these are the inner faces. Okay, that the boundary is really a simple polygon. Okay, so you do not allow the boundary to have pinch points like this. Okay, this, for instance, is not a triangulation with a boundary, whereas this really is. Okay, it's a triangulation of a pentagon, and you can allow more triangles like this. Okay, and we will call inner vertices the number of vertices that are not on the boundary. Okay, oops. So by definition, we let m, the size of m, to be the number of inner vertices. And this is going to be the size parameter for us. Okay. Now we define a law on these triangulations in the following way. So remember that last time I gave an explicit formula. So there is formula for the cardinality of triangulations with a boundary with n inner vertices, and the triangulations of an m-gon. And so again, I gave the explicit formula last time. I'm not going to write it again. But what you can do with this formula is take asymptotics as n goes to infinity. And if you remember, it was a formula defined in terms of a quotient of factorials. So by using Stirling's formula, it is not difficult to show that the asymptotic behavior is some constant c that depends on m times some exponential factor which turns out to be 27 over 2 to the n times n to the minus 5 halves. Okay, so this is a fact. And now, what you want to do is we let mu m be the law on the set of all triangulations with boundary size m, triangulations of an m-gon, such that the probability that a map sampled according to mu m is a given map m is equal to alpha to the power, the number of inner vertices of m, and divided by okay, z of m. Okay, so there may be little, okay, let me call the map T, okay, for triangulation, so that we have really two different letters. Okay, where alpha is some positive parameter and Zm is a normalizing factor. Okay, which a priori depends on, of course, on alpha. Okay. Now, what is this normalizing factor? You see that Zm is nothing but the sum over all triangulations of an m-gon of alpha to the t, number of inner vertices, and this is the same as the sum for all n of alpha to the n times the number of triangulations with n inner vertices. Okay, and therefore we see that this makes sense if and only if alpha is less than you know, the radius of convergence of this series, which is the inverse of this exponential factor. Okay, alpha less than 2 over 27. It actually also makes sense for alpha equals to 2 over 27 because of this decay, which is still summable. Okay, so in fact, and this is the reason why I didn't put an alpha in the notation before. From now on, we always fix alpha to be equal to 2 over 27. Okay, so you can call that, if you like, it is critical in a sense, you know, in the very weak sense that it's defined for alpha less than this, you know, for values less than that, and it stops to be defined for values that are bigger than that. Okay. Okay, so we call mu m the Boltzmann law, really critical, if you like, Boltzmann law on the set of triangulations of an m-gon. Now, this law satisfies, in fact, a very interesting property, which is a kind of branching property. Okay, so this law satisfies an interesting branching property that we can explain in the following terms. So let M be an element of, you know, be a triangulation of an m-gon with some number of inner vertices. And I want to to think of this triangulation. So I just draw the m-gon and look at the root, which is somewhere here. And let's assume that M is in the set that I'm going to call A, which is the set of triangulations such that the inner triangle adjacent, incident to the root edge is incident to an inner vertex. So what does that mean? So let's imagine for now that I don't know what's inside this polygon. There is some triangulation, okay? What I'm just going to tell you is that M is in this set, meaning that, so the M-gon is, if you like, the outer face here, but on the other side of this edge, I know that there is some triangle, and the only thing I'm telling you about this triangle is that it is incident to an inner vertex of the triangulation. Okay, it's not on the boundary. Okay, so this is the set A. So in this case, okay, I will call M prime the remaining part of M. Okay, so in this case, the remaining part of M, namely M minus this triangle incident to the root, so really the inner triangle. This distinction about inner triangle is just that the M-gon itself could be a triangle if M is equal to 3. Okay. So the remaining part is an element, a triangulation of, well, an M prime gon with M prime equal to M plus 1. Okay, I remove one edge and I add 2. Okay, so an M plus 1 gon. Okay. And in order that this makes sense, you should really have a routing convention. So, with some routing convention. So here it is, you can fix this convention. For instance, you can always take the root to be that edge. Okay, that would make sense, or that edge. But in fact, you could take any edge, like depending on, you could consider to be rerouted at the kth edge after this edge. You can do that if you like. Okay, but you sort of fix the convention. So that's one possibility. But there is, of course, another possibility for the root triangle, the inner triangle incident to the root, which is that it is all its vertices are incident to the boundary. Okay. They belong to the boundary. Okay. So we also let. So on the other hand, if M is in the set I'm going to call this set BK. So the set of triangulations such that okay, so I'm going to call that the root triangle, okay, in order to make this shorter, has its third vertex on the boundary, and I want it to be, let's say, k edges away from the root edge in a clockwise order, say, or counterclockwise order. So here this means that I have my polygon like this, okay, with the root there, and the third vertex, meaning the one that is, distinct from these 2 points, is also on the boundary. So I have a triangle like this, and it is k edges away. So by k edges, I mean you count these edges here, like 1, 2, 3. Okay, so in this case, k is equal to 3. Okay, and actually here k is restricted to 1, 2. That's right here, 1, 2, up to n minus 2. And the reason is that the reason why you cannot set k to be equal to 0 or m minus 1 is that there are no self loops. Okay, so it's not possible. This vertex has to be distinct from those two. Okay, so that's one point where I use this fact. And then in this case, I have really two remaining parts, okay? I have maybe a first map here, M1, and a second map here, M2, okay? So we call M1 and M2 the remaining parts. And now these are triangulations of a k plus 1 gon and an m minus k gon, respectively. Okay, so M1 is going to be always the one that is immediately to the right of the root triangle, and M2 the one on the other side. Okay. And again, you adopt some routing convention. For instance, you root there and there. Okay. Okay, so now with these conventions, we can state the branching property. So proposition. So it holds that mu m of A, so the probability under the Boltzmann distribution that you are in this set is equal to alpha times z m plus 1 divided by zm. And conditionally, let's say under the conditional law mu given A, the remaining part has distribution mu m plus 1. And similarly, mu m of bk is also explicit, given by zk plus 1 zm minus k divided by zm. And under mu m conditioned by bk, the remaining parts are independent with law mu k plus 1 and mu m minus k, respectively. Okay? So it's a very nice branching property. Okay? If you happen, let's say, what's behind this property is an idea that we are going to use a lot in a couple of minutes, which is, in this situation, you imagine that you don't know the map. You know, you want to sample, if you like, a map with distribution mu m, but you don't want to sample it all at once. You want to sample it recursively. So you don't know what it looks like, but you know the probability that the root triangle looks like this. Okay? And let's say that this happens. It has a certain probability given by that formula. And conditionally on the fact that it happens, then what you just have to do now is to sample a Boltzmann distribution with a slightly larger domain, okay, slightly larger boundary. And similarly, you know exactly what the probability of this event is, and in this case, you have to sample two independent Boltzmann maps. Okay. So it is actually a concrete procedure if you want to sample a map in practice. There is just something that I should mention here, because it looks like the procedure I've told you never stops, right? It seems that whatever the size of the boundary, I'm always going to continue sampling maps, and that doesn't make sense because Boltzmann maps, the law mu m is a law on finite triangulations. Okay, so what's the problem here? Well, note that there is a special case about the law mu2. Okay, the law mu2 assigns a non-zero weight to this very particular map that we've allowed as the unique element of a family of triangulation of a two-gone, but with no inner vertices. Okay, if you like, it's a triangulation of a polygon of degree 2, but in which there are no inner vertices. So this means that these two edges are glued together. Okay, so the probability of this map is strictly positive, and that means that there is a possibility that if you if one samples a mu2 distributed map to fill in a hole with boundary size 2, then there is a strictly positive probability to close this hole and stop. Okay? If you want an analogy with branching processes, it's what happens when you arrive at leaves of family trees of branching processes. With probability p0, a vertex has no children, and that's what happens. And this means, for instance, that this triangle was incident, for instance, to this third vertex, and instead of putting a triangulation, a non-trivial triangulation here, we just decide to close this edge, meaning that this third edge is really the same as this one. Okay? Okay, so let me prove this proposition. And it's, in fact, really immediate once you see it. So let M be a map in A. Then let's compute the probability that M is actually sampled by mu M. And by definition, this is alpha to the number of inner vertices of M divided by Zm. But now let M prime be the remaining part. Okay, in the sense of this blackboard. Okay. Then you see the remaining part has one inner vertex less than M by definition. Okay, because this vertex now is really on the boundary of M prime. So therefore, I can rewrite this in the form alpha to the M prime divided by Z M plus 1 times Zm plus 1 alpha divided by Zm. Okay, and I'm done. Okay, I just, I'm done because here you recognize mu M plus 1 of M prime, which means that the law of M prime is that of if you sum over all possible M primes, okay, if you sum over all possible M primes, this will give you mu M of A, and this will be 1 times this probability. And once you know that, you can divide by that and obtain the conditional law. Okay. And similarly, if M is in BK with remaining parts M1, M2, then mu M of the singleton M bar, well, it's just alpha to the M1 plus M2, because now the number of inner vertices of M, I haven't taken out any inner vertex in this situation. So the number of inner vertices of M is equal to the number of inner vertices of M1 plus the number of inner vertices of M2 divided by Zm. And you rewrite that in the form alpha M1 alpha M2 divided by Z k plus 1 Z M minus k times Z k plus 1 Z M minus k divided by Zm. And again, you're done because you have a product form here. Okay? And of course, the important thing here is that this is something that I didn't mention clearly here, but if you are k edges away from the root edge, it means that you are bounding a polygon of degree k plus 1 here, okay, and m minus k there. Okay. So again, I'm just going to comment again on this proposition. So this proposition can be used to effectively sample a random map with law nu n. And the idea is that we sort of peel the root triangle of the map M and then reveal the remaining parts. Okay? And this idea of peeling, so it's called a peeling process. So it originates in a work by Angel in 2002. And the idea comes back to ideas of physicists in the mid-90s, in particular Ambjorn, Watabiki, and others. Okay, so there is really a nice idea about this, that again the map is considered to be unknown, and you reveal it progressively. And if you think about it, we are very close to ideas like the domain Markov property. You know, it's something that is really similar to, for instance, an SLE process that you grow in a kind of progressive way. You unveil it progressively, and this is something that is really analog to that. Okay, and another point that I want to make here is that when I say we peel the root triangle, really we could peel any other triangle incident to a boundary edge. Let's say as long as we do this in a non-anticipative manner. Okay, so if you like, if we want to think about this proposition as the basis of an algorithm that reveals triangles one after the other, clearly there is nothing special about the root edge. Again, you can change the routing convention as you like, but you have to do it in a way that depends only on the first steps, you know, on the first steps of what you've done so far. Okay, and maybe some extra independent randomness. For instance, you can choose a uniform random edge on the boundary. Okay, that works just as well. Okay. And this freedom about the peeling process is something that is very important and very subtle, because you know there is something very curious here, which is you want to sample a Boltzmann map. You start revealing a triangle with some algorithm, any algorithm. You choose a boundary edge, reveal this triangle, then maybe choose another boundary edge, then maybe choose one that is close there, one that is there, and so on and so forth. Whatever the choice you make here, you are going to sample always a map which has the same distribution. Okay, so if you like, this idea of the choice of where you go is a bit similar to the idea of local sets. Somehow you are always exploring the same underlying object, but you explore it in a kind of progressive way. Okay, so when I say non-anticipative manner, you could of course formalize this in terms of using random variables that are measurable with respect to the filtration generated by the peeling process. Okay, so one other very nice aspect of this proposition is that it passes very nicely to the limit. Okay, so this proposition allows to pass to the limit as m goes to infinity quite nicely. And why is that? Well, let's look just at the probabilities of these two elementary events. Okay, so note that, okay, so this is something that I maybe didn't comment, but there is a, so note that there is the exact formula for Zm, and that should not surprise you. Okay, Zm is really a generating function for an expression defined in terms of quotients of factorials. So it shouldn't be too surprising that there is in fact an explicit formula for this, and this formula is given by 2m minus 4 factorial divided by m minus 2 factorial n factorial times 9 over 4 to the, I think, m minus 1. Yeah, that's right. Which is equivalent, as m goes to infinity, to, you see this 4 here simplifies with the factorial, so you get a 9 to the minus m times some constant divided by m to the 5/2 again. Okay, again by the Stirling formula. So therefore, mu m of A, well, given by this formula here, so alpha Zm plus 1 divided by Zm, it converges as n goes to infinity, m goes to infinity, sorry. These polynomial terms, they do not matter in this quotient, and only the exponential term matters. Okay, so you get alpha times 1 over 9. Okay, and this is 2/3. Okay, because alpha is 2. There's something. Oh no, that's m plus 1.
Like to the m.
To the plus m. Sorry. Thank you. 9 alpha. Thanks. Okay. So mu m of alpha converges to some limit, and similarly, for a fixed k, mu m of bk, which is z k plus 1 z m minus k divided by zm, well, it converges to, so this zk doesn't change anything, and then we have a shift of minus k, so we get 9 to the minus k times z k plus 1. Okay. Now, this very strongly suggests, although it does not directly prove, that there will be a limiting object for these Boltzmann distributed maps as m goes to infinity that can be described by a peeling process in the following way. So this suggests that as m goes to infinity, mu m converges in the weak sense to some limiting law mu infinity, where mu is a law on triangulations of an infinite gon. So which I want to picture really as, you know, maybe a half plane bounded by the doubly infinite chain of vertices, which is rooted somewhere. Okay. That can be sampled by peeling. Okay, so here now let me state the theorem, which is that, so indeed it holds that mu m tends to mu infinity, where mu infinity is characterized by the following properties. So the first property is that mu infinity of the event A. So here now by A, you see that when I defined the event A or the event B, they did really depend on M, okay? But I made the dependence on M completely explicit. And here again, this set A is going to be the set of all triangulations of this doubly infinite M-gon, this sort of infinite face bounded by an infinite line, okay, doubly infinite line. And here the event A is going to be the set of all maps such that the root triangle is incident to an inner vertex, okay, a vertex which is not on this infinite boundary. And this should be the limit which is over there, which is 2/3. Okay. And given this, the remaining part has law mu infinity. Second, mu infinity of, okay, so I'm going to change a little bit notations here. So I'm going to call BGK the event that the root triangle is incident. Okay, let's start maybe with BK for droite. So the root triangle is incident to the boundary. The third vertex is incident to the boundary. K edges away from the root edge. Okay. So this is given by 9 to the minus k times z k plus 1. And given this, the infinite remaining part is distributed according to mu infinity, and the finite one has law mu k plus 1, and both are independent. Okay, whereby infinite part, I mean the part with this infinite boundary, and by finite part, I mean this part. Okay? And thirdly, same for mu infinity of bkg, which now means that you are incident to the left k edges away from the root edge. Okay? And it's almost complete. The statement is almost complete. So for mu infinity is invariant by rerouting. Okay, if you decide to reroute the law, I mean to reroute the map one edge to the right of the root edge, you obtain something with the same law. Okay, which means that if you reroute k edges away to the right or to the left, you obtain the same law. Okay, clearly. Okay, so this is what I call invariance under rerouting, which is of course a property that we get from the discrete side. And so there is actually a very nice paper by Omerangel and Gourab-Rai, where they prove that, in fact, as soon as you have this invariance under rerouting and this, so the property that the remaining part, the infinite remaining part, has law mu infinity is called the domain Markov property for these objects. Okay. So if you have the domain Markov property, the invariance under rerouting, and the fact that this event has probability 2/3, then it actually suffices. It completely identifies also the law of mu infinity. And if you fix another probability, you get another interesting family of objects. I'm not going to discuss them here. Okay, so clearly I won't have time to show you the proof of this result, but I can at least give you an idea of how you can prove that. So there are several ways to prove this result, but so this can be proved along the following scheme. So first of all, show that mu m of, so they are going, okay, let me call that maybe capital M, okay, I don't know, capital T index T converges to mu infinity T, where T sub T is the set of all triangulations of the infinite gone that have T as, let's say, a ball of radius R about the root. Okay, so that's really for every fixed T. So what does that mean? It means that you are going to fix, if you like, the form, the shape of the ball of radius R about the root that you want your random map to be equal to. Okay, so for instance, do something like this, and then this is the ball of radius 1, say, and then maybe the ball of radius 2 is going to be something like that. Maybe something like this. Okay, so you fix this shape, and you show that mu m, the probability that this is the ball of radius 2 in mu m, converges to mu infinity So okay, so at this point, of course, you don't know that mu infinity exists. Okay, so you want to show that it converges to some limit. Okay, so that you want maybe to call mu bar of T sub T. Okay, and a way to do that is to use the Peeling algorithm. Okay, so in order to do that, you can fix an exploration of the map T. So for instance, you can fix a spanning tree, something like that, maybe. Okay. Fix a spanning tree of the dual graph of T, and you explore this spanning tree in depth first order. Okay. Then every time you encounter a new edge, you reveal the triangle incident to that edge. And the geometry of T will tell you exactly what the probability for the corresponding event corresponding to TT to happen must be, right? So here, for instance, you know that under mu m, in order to unveil this triangle, this will happen with a probability alpha z m plus 1 over zm, where m is the size of the boundary, okay? Then you know that in order to unveil this new triangle, the event A must happen inside a slightly bigger boundary, so you must get alpha z m plus 2 over zm plus 1, and then continue, okay? So you know exactly this probability. It's given by a finite product of probabilities of that form, okay? And individually, the terms of this product converge to limits, okay? So, this quantity is also a finite product of probabilities that are probabilities of this form, okay, and that correspond exactly to mu m. And in particular, what is nice about this, and which already tells something about the peeling process, is that what you obtain in the end does not depend on the choice of the exploration of T that you made, okay, because in the end you always get this quantity, which is independent, of course, of the choice of exploration of T. It just depends on T. Okay. So here, this implies that mu m converges to a limit mu bar, but it converges only in the vague sense, okay? In the vague topology as m goes to infinity. Why is that? Well, okay, this is in the vague sense, of course, for the local topology on the family of all maps, possibly infinite maps. And what do I mean by the vague sense? You know that a sequence of measures converges weakly to a limiting measure if mu m of every continuous and bounded function converges. And if you think for a while about this, what we have here are indicators of these events, and these are indeed continuous functions, but they are not, they do not generate, if you like, all continuous and bounded functions. For instance, essentially you cannot recover the function identically equal to 1 using these events. Okay, so what's missing is that mu is a probability measure. What we just know is that mu bar of m a priori is a non-negative measure, but with total mass less than or equal to 1. Okay. So of course I went very quickly through that, but given the definition of the local topology, so remember that two maps are close in the local topology if the balls of radius r coincide for a very large r. It shouldn't be too surprising that it suffices to know that these quantities over there, mu m of t, index t, converge to some limit to show convergence of measures. Okay, you have sufficiently many, if you like, continuous functions or sufficiently many events to conclude in this way. Okay, but again, the thing is that you still need to show that the limiting measure is a probability measure. And two, so the fact that mu m of m is equal to 1 can be obtained by the peeling algorithm. Okay. Described in the statement. Of the theorem. So what I want to say here is that sort of any limiting measure mu bar will have to satisfy these properties as the limit of the measures mu m. Okay. The only thing again is that We don't know whether they are probability measures. So if you can show that using these properties, you always sample a map, an element of M, then you are done. Okay? And so the idea is that you can show that the peeling process almost surely samples an element of M. And for this, you can reveal the balls of increasing radia. So radia 0, 1, 2, 3 consecutively, successively. And let me just give very quickly the idea, because I want to, at least state and prove one property of this limiting space. So let's imagine that you want to reveal the ball of radius 0. It's already done. Okay, good. Now let's reveal the ball of radius 1. Well, what should you do? Well, you look at the root vertex, and you look at the triangle which is incident to that edge. Okay, and that may be this triangle. Okay, so good, you already showed that this vertex is in the ball of radius 1. Then you continue, always peeling the edge that is incident to the only vertex at distance 0 from the root, which is the root itself. And maybe you find something like this. So this is also at distance 1. And you again peel this edge, and maybe after some point, you swallow a region like that, meaning that this is at distance 1. Okay? And here, for the parts that are here, you can, for instance, immediately sample Boltzmann distributions with the proper boundary size here. After you have swallowed this vertex, clearly all the vertices at distance less than 1 from the root are all within this finite region. Okay, because all the triangles that I'm going to draw subsequently are outside and are linked by an edge to vertices at distance 1 from 0 only. Okay? So you can continue now by peeling this vertex. We know that this is at distance 2. Okay? So we can reveal now this triangle, which is at distance 2, then reveal maybe that triangle, fill up this region, okay? And here at this point, well, the ball of radius 2 is inside this region clearly. So the only thing you have to show is that for any vertex, you will, in finite time, sort of peel off this vertex in the sense that you will completely surround it with triangles. But now that's really clear. So the idea is that any vertex is sort of peeled off of the map in finite time. And this time is really stochastically dominated by a geometric random variable with some parameter. Why is that? Well, from any vertex, if you peel the edge that is left to it, you will have finished exploring this vertex as soon as you have an event of this form, some event of the form bk. Okay? bdk, really. Now, what's the probability for some event bdk to happen? It's 1 minus the probability that A happens, okay, which is 1 minus 2/3. That's the probability of A, times 1/2, because when A does not happen, clearly the triangle can either go to the left or to the right. Okay, and this is 1/6. Okay, so after geometric number of trials, you will eventually completely swallow this vertex. And so what you are doing is you are really drawing the balls of an infinite map. Okay.
So, Gregory, I completely missed something. What do you mean by μm of TT?
So μm of TT is the probability, if you like, μm of TT is just the probability that the ball of radius r inside a μm distributed map is equal to the fixed triangulation T. Okay, so this is, I know my notations maybe are not very good, but this is the triangulation T, the finite triangulation that is a possible ball of radius r in the map, if you like. And this is the probability that, the set of all triangulations I said of the infinite gone. Yeah, that's not so good. Yes, so, okay. I guess it's okay if I write it in this way. Is that okay, or no, not quite? So okay. I can go over time, I'm the last lecturer, so I have plenty of time. Any questions? You want a cup of tea? No, so maybe another chance that I explained that better, or?
I can talk to you later.
Okay. All right. Okay, so at least I've sketched the proof of the convergence of μm to this limiting Boltzmann map, to this limiting infinite map. And as you see, this infinite map has this very nice sort of domain Markov property associated with it. Okay. Now, what I want to finish with is percolation on, UI HPT, so it's uniform infinite planar or plane, really half plane, sorry, triangulation. And what is UHPT is a mu infinity sample map. Okay, and I will really do site percolation. Okay, so I think at this point you all know what percolation is. We had a series of very beautiful lectures, and I think almost all of them had some percolation at some point, or at least in the background. So let's do site percolation in the UI HPT, and as we are going to see, it's actually in many respects much simpler than percolation on the regular lattices. And the reason is that, as you know, what's important about scaling limits of percolation is that you have asymptotically a domain Markov property for SLE, the limiting curves. And in fact, here, the domain Markov property is already in the geometry of the lattice in which you are doing percolation. So it's already there. And as you will see, it makes things extremely simple. So again, consider P index P to be the probability for, if you like, mu infinity dt times, Bernoulli percolation on, okay, so that would be Bernoulli P to the power all the vertices of T. Okay, this is the measure under which I first choose a map with law mu infinity, and then consider Bernoulli site percolation with parameter P on the vertices of T. Okay? And the theorem, which is due to Angel, is that the critical, the percolation, okay, how do you call that? The critical percolation threshold is P equals to 1/2, in the sense that the probability under P that the root is connected to infinity by a black path. Okay, so I say, P is the color of black, and 1 minus P is white. Okay, I think it's a common convention. The probability that the root is connected to infinity, meaning that its connected black component is infinite. This is strictly positive if and only if P is bigger than 1/2. Which, in passing, tells you that at p equals 1/2, you don't have percolation. Okay. Now, let me show how you can prove such a result. So actually, there are very nice generalizations of this result, and in particular in a recent paper by Omer Angel and Nicolas Curien, and they identify many other percolation thresholds for either the UI HPT or variants of these models replacing triangulations with quadrangulations. And there is also a very recent paper by Loïc Richier, who is a student of mine, and he actually, so this theorem was stated with a kind of particular boundary condition, which is all white except the root vertex, which is black. And there is a comment in the paper by Omer and Nicolas about, a more general boundary condition, more natural one maybe, which is free everywhere. Okay, you don't fix the boundary condition. And actually, so the approach by Loïc is kind of robust and allows you to deal with such boundary conditions. So this is the one that I'm going to present here. So sketch of proof. So the idea is to explore the percolation interface using peeling. And here you will see that the freedom in the edge that I want to peel is going to be very important. So let's start from the infinite boundary. And let's say, of course, that the root vertex is black. Otherwise, there is nothing to do. Okay, so we condition on this fact. And we don't condition at all on the other vertices. Okay? So what we do is reveal, so we are going to grow, if you like, a black family of vertices, a connected black segment of vertices on this interface. Okay? And to do that, we reveal the vertex of the boundary to the left of the root, or more generally of the explored segment. So if black, do it again. Okay, meaning that, let's say that this is black, this happens with probability p. Well, okay, I'm very happy because I know that there is at least one other vertex in this black component. So I'm going to do it again, and it's black. Very good. So I have 3 vertices in my boundary component. Okay, and this happens with probability p, and I get, in this case, +1 black vertices. And now, if it is white, then possibly this white vertex is going to block my boundary components. So what we do, we peel this white vertex in the sense that I introduced before, namely, you look at this edge and peel the triangle there. So maybe this happens, okay, and I don't want to reveal now the colors of the vertices that I'm meeting here. I want really always to peel the edge which is to the left of this white vertex. So maybe I get something like that. Okay. And then again, maybe another vertex which I don't want to know the color of. But after some time, eventually, I will swallow some of the black vertices there. Okay. Okay. So peel this white vertex. So until some part of the black segment, it's really until some event A decay happens. And when it happens, well, I'm going to lose with probability, so 1 minus p, which is the probability that this is white. I'm waiting until this event happens, so I'm quotienting by the probability that some AKD happens. Okay, and AKD happens. It happens with probability 9 to the minus k times zk plus 1. And in this case, we lose k minus 1 black vertices. Okay, if I have two edges, then really I lose only this one, okay, because this is still in my boundary. Okay? And then after this is done, you continue. Okay, this is really the algorithm. Now, and I'm going just to need 2 minutes to conclude. When does this algorithm stop? Well, you see that on my picture I can still continue because I still have a boundary which looks like a family of black vertices surrounded by a boundary vertices which I don't know the value of. Okay? But after some time, what can happen is that you have these black vertices, and then you encounter this white vertex. You start peeling it. Okay, so this is free, maybe on the other side here, free. And then after some point, maybe you swallow all the black segments. And in this case, if it so happens that this vertex is white, then you know that there cannot be percolation, okay? Because this edge between these two white vertices blocks this black path to go to infinity, from going to infinity. Okay? So if the length of the black segment reaches 0, then rho is not connected to infinity with probability 1 minus p, which is a probability that the revealed vertex here is white. Okay. Now let's look at what we have. Well, we really have, what's the behavior of the length of this black segment is really a random walk. Okay. It does +1 with probability p, minus k minus 1 with probability 1 minus p times 9 to the minus k zk plus 1, divided by the probability that some ak happens, but we already computed this probability. We know it's 1/6. Okay, so it's just 6 times this. Okay, so we have a random walk with these step distributions. Okay, and so you can compute the expectation of one step, which is equal to p minus 6, 1 minus p, sum of the k minus 1, 9 to the minus k, zk plus 1 for all k. And zk is explicit. You can compute explicitly this series, and what you end up with is 2p minus 1. Okay. And so therefore, if p is strictly bigger than 1/2, the random walk drifts to infinity. So there is a probability that the black segments, so the random walk, hence the black segments, never reaches 0. And if it never reaches 0, well, it means that it goes to infinity. It's a random walk with positive drift, and it means that the cluster of the origin has infinitely many black vertices. And now, if p is less than 1/2, then the black segment, then the walk oscillates or drifts to minus infinity. And clearly, it means that the black segment, at some point, well, it cannot take negative values because it just means that the walk somehow swallowed the black segment. It's going to happen infinitely many times. Okay, so the black segment will be swallowed almost surely, and then with probability 1 minus p, the process stops. If with probability p I find the black vertex, then I resume. Okay, I resume with the exact same algorithm until the black segment is swallowed again, and then with 1 minus p, probability 1 minus p, the end. Thank you. Any questions?
Just a small comment, perhaps, that the ideas of killing in some form go back even further to Tat, which used these recursions to derive the original numerative formula.
Yeah.
And in some way, the ideas go back to that even.
That's right.
Before the physics.
Yeah, I think what's specific to these ideas is the algorithmic, the algorithmic way in which you can use them, and in particular the fact that you have a complete freedom in about which edge to peel. But it's true that when you want to do enumeration of triangulations, then you use also this kind of recursive decomposition techniques. It's really the building block for enumeration results. Absolutely right. Okay, it was a pleasure. Thank you.